All right, so we're going to start talking about work and energy. And we'll get to energy with the next lesson. But they're related, and so we'll get work and energy. Today we're going to focus on work and what we mean by work. So it doesn't mean what you think it means. We have a scientific explanation for it. And it's basically, it has to do with motion. So suppose I had a box that was sitting on the floor. And if I displace this box to say here, so we have some displacement. Then I've done some work on it. So I've changed its position, and that's kind of key. So we're going to need to have a displacement of some sort. And we do this, if I were going to move it, I would do it by applying some force. Like maybe I'm just pushing on it, I'm over here. Pushing on it. And so this force, by applying the force over this distance, I would create work. I would do work on the box. So a couple things. I guess first we can just define work, what it is. So work is going to be defined as any parallel force or component times the displacement. That's it. So this force you can see is being applied parallel. It's parallel or anti-parallel to the displacement. So the displacement is in this direction, so is the force. So we would just multiply the force times the distance, and there you go. There's your work. The units on this thing are joules. So we just use J. Those are joules. And equivalent is a Newton meter. So Newton meter is what we actually get, but we just call that a joule, a Newton meter. In this case, since the force is in the same direction as the displacement, so force and displacement are the same direction, then we have positive work. Because it would be like you could see like it would be positive force times positive displacement equals positive work. Or negative force times negative displacement, well, negative times negative is positive work. Whereas if it's opposite, so force and displacement are opposite, then it's negative work. So if I have negative force and positive, you can see I get negative work. So when I get negative work or positive work means that energy is increasing. So the energy goes up. Negative work means the energy goes down. We're taking energy out of the system. Let's see what a positive force negative delta x is negative work. Okay, so that's your in general, whether we're doing positive or negative work. The math will take care of it. So the other thing that we need to know is what I meant by parallel and anti-parallel. So if something is this way, so we'll call that vector A, vector B, and vector C. So all of these in geometry, you would say they're parallel, but because they're vectors, these are different vectors. So B is parallel and C is anti-parallel. What it means is it's parallel, but in the opposite direction, anti-parallel. So either one of these. But what happens if the force is not is not parallel? So it's at an angle. So let me draw a picture of that, and then we can talk about that. So again, we have the box, and it's going to be displaced some distance, but now I'm pushing down on it. So again, we're going to have some displacement here. If you don't have displacement, there's no work done. That's another key. Okay, so now I'm pushing down at some angle theta. So I have a force. I'm going to exaggerate it a little bit, but we can imagine that the force is going down like this. So that's my force. So you can see this force is not parallel. And so what we can do is we can break out components, and we can find a component of this force that is parallel, and that's what we want. So if I draw components, I can see that I get an F in the X direction and F in the Y direction. And then this would be some angle right here, theta. So what you can see is it's this component right here is parallel to my displacement. And so that's the one that I want. And we have to define it in terms of this force. And so Fx is going to be the force cosine theta. So this would actually be the parallel force. So we can add that on, because if it's not parallel, if it's at some angle, well, then it's just going to be the force times cosine theta. That's the piece that's parallel times the displacement. And we can rewrite this, we can reorder it. So that's just force times displacement times cosine of the angle between, this is between the force and the displacement vectors. So the angle between them. Okay, so it looks like a whole bunch of stuff, but it's just this and this and this. So it's on your equation sheet. I'm going to rewrite it, but I'll show you where it is. So if you go down, sorry. All right, so right in here for mechanics, you go down and there's momentum and there's impulse or change in momentum. This is kinetic energy. We'll do that next, but here it's right here. So you can see work is going to be the force, the parallel force times the displacement, or the force times distance times the angle between them. So that's it. And then this is also a change in energy is what we're going to get. So it's similar to, this is actually similar to this one. Your change in momentum is force times time. This is change in energy is force times distance. Okay. I'm trying to think if, I think that covers the basics. So we'll go ahead and tack that on. Change in energy is work. So in fact, let me just summarize that again. So what we've done is we said the change in energy of an object, you don't need to worry about this part, we'll do that next, is the work done on or on the system. And that's going to be the parallel force times the displacement, or the force times displacement cosine theta, where theta is an angle between the displacement and a force. So theta. All right, let's do some, we'll do a couple examples. Pushing straight across is not very, it's pretty straightforward. So let's do some at an angle. So suppose I was pulling a box, I had it tied to a rope. So we're pulling with a force here at some angle 15. Okay. So if the force were 10 newtons and we pull for a displacement of 20 meters and the angle there is theta, so theta is 15. If we want to know the amount of work or the amount of energy that was put into the box, then we would just set it up. So the work is going to be the force, since it's at an angle, that's going to be d cosine theta. And then we just plug and chuck. So 10 times 20 times cosine 15, you put that in your calculator, you get whatever you get. And that would be in joules. And that would be your work. So it's actually really straightforward. I'm not going to do too much. You have some examples in the reading. I did want to do one that might seem a little weird. Okay, so an inclined plane. So suppose this has friction, theta. Okay, so we'll put some mass on this. Give it a mass of, say, 10 kilograms. Theta we'll put at, say, 30 degrees. And then the coefficient of, let's say, kinetic friction is 0.12. Okay, so what you're going to have to do is figure out all your forces. So we're going to have weight coming down here. And then we'll have friction moving backwards. So we're going to have some kinetic friction. Okay, so the question is, what's the total work? Okay, so to do this, we would say, well, the total work is going to be the work of the weight. So I don't want to put another W. We'll call it work of, I don't know, G of gravity. And then also the work of friction plus the work of friction. Okay. So this G, so what we need to do is we need to figure out what's the angle between this vector, the force vector, and this one right here. This is the displacement, because this thing's going to move this way. Let's say after, I guess I should have put that, delta x, let's do 2 meters. So we're going to release this, it's going to slide down. So what we want is we want this angle right there. Okay, so if you remember your, when we did inclined planes, we would do a triangle like this and like that. So you can see theta goes right there. So this angle right here is going to be 90 minus theta. So 90 minus 30 would be 60. So my angle is 60. So what I get is I'm going to get my force of gravity times the change in position cosine 60. And the 60 again comes from our force diagram. And then plus the work of friction. So friction is opposing it. It's going against it. So we're actually going to change that to a negative, because it's negative work. And it's the force of kinetic friction times the displacement. Okay, so that's my total work. Now we got to figure out all this stuff. So the force of gravity, well, that's mg times delta x cosine 60 minus kinetic friction. So that's the coefficient of kinetic times the normal times the displacement. So I know this. I need to know the normal force. So remember we did, when we did inclined planes, the normal force comes up like this and it's offsetting this Fy. And Fy in this case would be Fg cosine theta. So we're going to get mg times delta x cosine 60 minus the coefficient of kinetic friction times mg cosine theta, which is 30, times delta x. I hope you don't mind that I write it like that. I know people like to do that. I usually just leave it off. And then at this point now we can just calculate everything. So yeah, that's it. That would be your total work. I don't know what this value is. I'm not going to calculate it. So you just plug in your numbers and there you go. So anyway, that's about as complicated as it gets. Just breaking it out. Just remember, you got to figure out, if it's at an angle, you got to get the angle between the displacement and the force. So it's this angle over here that we care about. The kinetic friction, we had to get, we had to pull out the other side in order to get the normal force. But that's it. That's all I got for this.